colleagues. Gases, no fixed volume, no fixed shape. Their molecules have an extremely weak attraction to each other. Molecules move randomly, rapid motion, there's frequent collisions, but one interesting thing about gases is they are easily compressed. So when you think about us using oxygen, which oxygen is a gas, we can compress that oxygen and put them into tanks and cylinders. And that's why we have them available to us when we need to administer oxygen to a patient, because we can compress that gas and place it into a cylinder or into a tank. The atoms that are in these various structures do move. They're in constant motion. It's from their internal energy. Now, potential energy, that's the energy of position. Due to strong attractive forces, we see that makes up most of the internal energy in solids and liquids. Whereas gases that don't have a strong connection between the molecules and the atoms, they are constantly in motion. We call that kinetic energy, or at least most of that energy inside those gases are kinetic energy. Now, laws of thermodynamics. Now, thermodynamics simply can mean the science of studying properties of matter, which we're talking a little bit about today, or the speed of the reactions of that matter at various temperatures. And that leads us to the first law of thermodynamics that deals with the transfer of energy. Heat is the transfer of energy. So when two objects of different temperatures coexist, we know that heat will move from the hotter to the colder object until both objects are at the same temperature. 4 different ways of heat transfer, and we'll talk about each one of these. The first one, conduction. That is the main method of heat transfer among solids. It does require direct contact between the two objects. For example, me and my cold hands, if they were to touch your arm that's much warmer than my hands, the energy, the heat from your arm would move into my hand. But you would feel the sensation of what? Cold or coolness. We know metals have a very high level of thermal conductivity. That's why when you touch a metal, I don't know if I have a metal object truly up here, but if you touch a metal object, maybe the leg of the table's in front of you, they're cooler, and why they feel cooler to the touch, because metals have a very high degree of thermal conductivity. Convection, the mixing of fluid molecules at different temperatures. Okay, we can see this transfer of heat between liquids and gases, where we can see convection. Anybody that ever uses a convection oven, or even the heating systems in our home, where it's heated in one area and that heat is then moved or pushed through it via a fan, etc., to another area. We see it in healthcare or in respiratory care with an infant incubator, using convection as a means to heat the internal area of this infant incubator. Now, radiation occurs without direct contact between two substances. Radiant energy or radiant heat. Example would be the sun and how it warms up the earth or warms us up. Radiant energy. Now, in medicine or in respiratory care, we can see an infant radiant warmer, where the heat from this lamp at the top is turned on and provides heat down to where the child is, the infant, the neonate is. God bless you. And so an infant radiant warmer, example of radiation type energy. Again, the transfer of heat. Now, vaporization, that term, and maybe looking at this and looking at the lecture and the slides and eventually your notes later, it's going to be some terms. So just make sure terms are something you pay attention to. Those are very easy, if you couldn't tell already, very easy test questions for me to write. Where I give you a definition, what's the term? Or I give you the term and give you 4 different definitions to look at. So vaporization, change in state from a liquid to a gas. Now the term evaporation, that's going from a liquid to a gas. Heat's taken from the surrounding area near the liquid and cools the air. Best example of evaporation is when we exercise and we sweat. That sweat, that liquid helps to cool the air around us and keep our temperature down. Condensation, the exact opposite of evaporation, where gas comes back into a liquid form. We see that generally in the morning when we get up early before the sun has a chance to rise, and what's on the ground, what's on the grass, dew, or what's on our car, dew all over the car. That's a liquid that was in the air that is now changed from a gas into a liquid. All right, temperature is the measurement of heat. When we look at the temperature, that is the true measurement of heat. Again, results because molecules are colliding with one another. Gas temperature is directly proportional to its kinetic energy, meaning you heat an object, you increase the temperature of an object, you're going to increase its kinetic energy. All right, temperature scales. We'll talk a little bit about temperature scales, and I know coming up in another class we're going to talk about temperature scales and maybe having to figure out how to convert between Fahrenheit and Celsius. That is not today, that is not in here. Now I will say there's going to be another class you're going to have to learn to do that, but I'm saving it for that other class, not this particular one. I know sometimes when you're studying for things, you're like, I know I need to know that, but is it for this coming up test, or is it this other test in this other class on a different day? So make sure you do recognize in classes, especially this semester, we'll be talking about some like things in different classes, but some things you're responsible for in one class could be different than what you're responsible for in another. Let me go ahead and say, the term absolute zero. Now that is the temperature where there's absolutely no kinetic energy. No kinetic energy. Molecules cease to move, cease to vibrate, and that object has zero measurable heat. Regarding the temperature scales, anybody heard of the temperature scale Kelvin? That's what this is. 0 degrees Kelvin is absolute zero. Now you can read what's on the slide. Scientists have never been able to actually achieve it. They got close to it. So this is really, in theory, based on the third law of thermodynamics. Nevertheless, in respiratory care, we don't talk about Kelvin. We don't use that particular temperature scale. But we do sometimes use Fahrenheit and Celsius, and sometimes we do bounce back and forth between the two scales. I wish when it's all said and done we just had one and could move on from it and have, why do we have to be different here and using a different temperature scale, but nevertheless, it is what it is. So, 0 degrees Celsius is the freezing point of water. We know that's when water will then freeze and turn into ice. We know that at 100 degrees Celsius, that is when water will boil. And again, that water will change from a liquid state into a gaseous state. Now you can see also how that compares to Fahrenheit. 32 degrees Fahrenheit is when water will freeze. We know 212 degrees Fahrenheit is when water will boil. And we will, like I said in another class, have to learn how to convert between those two, but not in this one, not in this one. All right, all matter, whether it's a solid, liquid, or gas, can change in state. We know that, and here's my example of a solid, an ice cube. If it's heated enough, at some point the molecules will break free of that solid, that rigid structure, and change itself into a liquid. We know that's going to happen if we put an ice cube on the table just at room temperature. If I put an ice cube on the stove and raise the temperature, we know that solid will convert into a liquid. So some terms here with that. Melting, the changeover of a solid into a liquid. Again, if you remember that term melting, that temperature would be known as its melting point. Freezing, changeover of a liquid into a solid. So again, that water may be being frozen to be placed into the ice box or into the freezer. The temperature where that occurs is known as its freezing point. I don't think that's anything we didn't know already before today. And if it is, I'm happy I could teach you something about freezing and melting. Sublimation. So here's something you might not have heard of, or it's been a while since you've heard of this. Sublimation. This is transfer from a solid into a gas without passing through an intermediary stage like a liquid. And so I know it says solid to vapor. Vapor is a gas. So going from a solid into a vapor or gaseous form without turning into a liquid first. Best example, dry ice. Anybody ever mess with dry ice? Again, it's going to be October soon, Halloween. Oh yeah, kind of a cauldron looking, boiling thing. Again, what is dry ice? It's frozen carbon dioxide. Frozen carbon dioxide, if allowed to heat, will turn itself from solid into a gas without converting itself into a liquid first. All right, so some properties of liquids. Liquids can flow. We know they can take the size or shape of the container they're in, and we know liquids can flow. Liquids can also exert pressure. Now that pressure can vary with the depth of the liquid or even the density of the liquid, maybe what that liquid is composed of. Now the term viscosity is important to know. Viscosity, that is the force that opposes a fluid's ability to flow. Now viscosity is similar to how friction would be with a solid. If I'm trying to push a solid object maybe uphill, and it's that hill, the floor, the ground that I'm pushing on is creating friction. Well, viscosity is what leads to friction among liquids that can prohibit or slow down its ability to flow. Now, if I was to compare, and using the term viscosity, water to say syrup for my pancakes in the morning, which one has more viscosity? The water or the syrup? So again, you can say, well, it's that liquid is thicker, right? Thicker. Viscosity, thickness of the liquid that's there. Motor oil has different weights. Again, why all those different weights? Again, I can never remember what my car takes. I gotta look it up. Okay, I need this particular weight of oil. That's all related to viscosity. There's some oils that are very thin and some oils that are thicker. Again, depending on what our car is and what our engine requires, it may require different viscosity motor oil. Move on here. Blood has a viscosity that is 5 times greater than water. 5 times. So when you hear the old line, blood is thicker than water, it's not a lie, that is a true statement. Blood is thicker than water. Now, blood does contain water. Most of blood is water, but there's also other stuff in blood. There's cells, there's plasma, other things. And that's what leads to the viscosity of blood being a little bit thicker than just water. Again, 5 times greater. The greater the viscosity of a fluid, the more energy that's going to be required to make it flow. All right, so think about what makes our blood flow. What important organ do we have that makes our blood flow? The heart. Okay, so the heart. Every time the heart pumps, it pumps that blood. It pushes that blood through our body. Now our heart's designed not just to pump water, but to pump blood. So the heart's working the way it normally should, pumping that normal viscosity blood through our body. Now, in certain conditions, certain disease states perhaps can cause our blood to be a little bit thicker than normal. Now I'm using a term here that we might not have ever mentioned before, but polycythemia. Anybody know what the term polycythemia means?
It's like a greater amount of blood cells.
I hear greater, increase, amount, yes. Greater, increased amount of red blood cells. Red blood cells. So, if there's an increased amount of red blood cells, so there's more cells in the blood than there normally is, the blood is now thicker. Now, I will say there's certain diseases that can cause polycythemia. We see that sometimes with our COPD patients. You're going to get sick of me saying COPD because I use COPD as an example for almost everything. Right? So far, I have, right? There's going to be others, I promise. But just for now, COPD. Those patients with COPD typically, especially more severe stages of COPD, may chronically live with oxygen levels in their body that are less than ours. Okay, and that's I'll say that's their normal. That's because of the disease that they have. Their oxygen levels are a little bit less than ours. Well, the body's an amazing thing. The body will recognize that the tissues are not receiving the same amounts of oxygen that it used to prior to COPD causing this problem. The body will automatically make or create more red blood cells because it's the red blood cells, actually the hemoglobin in the red blood cells, that carries the oxygen in our bodies, carries it to the tissues that need it. And so the body will recognize, my tissues are not receiving the same amount of oxygen that it should, that it used to receive. And so is there anything the body can do? Well, the body can't increase its FiO2 or its concentration of oxygen, but the body can say, well, hey, I need to produce more hemoglobin, more red blood cells to be able to transport and carry more oxygen. And so it will. And so for those COPD patients, especially severe COPD patients, they may live with blood that is polycythemic. And again, it's a way for the body to be able to deliver more oxygen than it normally was able to the tissues. Now that's great, that's amazing, that's wonderful. Thank goodness for that. However, on the flip side, what happens to the viscosity of the blood with polycythemia? It gets thicker, right? More viscous. And so what important organ has to pump that more viscous blood? The heart. And so over a period of time, could be several years, number of years, the heart's working extra hard when before it never had to work that hard. So it's a catch-22. Yes, good thing we have more hemoglobin to deliver more oxygen to the tissues that need them. However, we're putting added stress on the heart. And so we will talk about this in time, that we do see sometimes with our COPD patients, them develop congestive heart failure later in life. And it's again, double-edged sword. Now we have to treat the CHF that they have, and it's manageable, it can be treated, but that's what led to their heart failure, because we put the heart, the patient, I guess technically did, make the heart work even harder. Now, I don't remember if we talked about this in the past, and if we have, I apologize, but I know we did. I gave an example that if I'm an endurance athlete, which in case you didn't notice, I am. I know. Got that on video. Thanks, Jeff. You'll edit that out for me, right? Appreciate it. Got my back. That for the endurance athlete that goes to train at altitude, and again, going to altitude, now you make your body have a little bit less oxygen. What's the body's natural response? Make more red blood cells, make more hemoglobin, so you can transport and carry more oxygen to the tissues that you need when you're competing in the event that you're training for. But what could happen to that athlete in time? They are always doing this. They're always creating more viscous blood. Now, over time, that's going to put added stress on their heart. Again, so, okay, you want to win that gold, you want to win that competition, but what's the long-term consequences of putting that added stress on your heart?
Is it like, so there's like athletes that will like have blood like taken out, like a pint or two of blood, and then they'll save it and then reinsert it back in? Is it kind of like the same thing?
It's exactly the same thing. So what they're doing is putting in more red blood cells, even if it was originally their own, again, so their body can do what? Carry more oxygen. If, again, I think I used this example before, you and I are, physically, athletically, the exact same. The only thing different, you have more red blood cells, more hemoglobin than I do. We're competing, I can only go so far. You can go much further in our competition because you're able to carry and transport more oxygen to the tissues. And so that's why, the International Olympic Committee and other organizations will test for that and see, I know you don't have COPD, and because there's no way you should be polycythemic, they can see that, yes, this athlete has an abnormally high red blood cell count. what did they inject? Blood doping, you may hear that term used in those endurance athletes. That's what they're doing. The bicycling champion, help me with his name. His name was Lance Armstrong. Thank you. That was one of the things he was accused of, and I don't know the story behind it, other than an endurance athlete, bicycle athlete like he was, an unfair competition against his opponents who weren't doing that, and I'm sure in a lot of endurance competitions, he's probably not the only one that's ever done it or will continue to do it in the future, but that's just an example. But I always say that's going to put so much added stress on their heart over time. Yes?
If somebody's taking blood thinners, will that also affect the heart in an opposite way?
It could. Blood thinners generally are to prevent clotting from happening as normally as it should.
Okay.
And so the problem with blood thinners, to keep obviously the blood thinner, is so there's no obstructions, leading to a pulmonary embolism or a heart attack. It's changing it, yes. Yes. Or leading to a stroke or something like that. But it's one of those things with blood thinners, they just nick themselves. They're going to bleed all over the place for a lot longer than, say, you or I. So things they have to be aware of. All right, again, still talking about properties of liquids. So the term adhesion, this is the attractive force between unlike molecules. And again, this attraction is at the surface. So if you look this test tube represents adhesion. So look at the surface. Notice how this water, okay, there's water in here. At the surface, you see this concave shape appearance. It's not flat across, it's concave, because there's an attraction at the surface between the molecules in the water wanting to hug the walls of this tube. Okay, so that's the adhesion, the attractive force between unlike molecules, as opposed to cohesion, where you have this liquid where it doesn't want to hug to the unlike molecule, it wants to hug to itself and stay attached. We call that cohesion, and it has this convex shape, a liquid like mercury. Now, I will say this, we should not be ever playing with liquid mercury, but if anybody ever has, Jeremy has? Yeah, his hand was up, sorry, I set him up for that. Go ahead, Jeremy.
So is adhesion what happens when you talk about surface tension?
That's part of it, yep, that's part of it. But with mercury, again, I don't encourage anybody to ever play with liquid mercury. It's not something you're supposed to touch or handle. But me being a 16, 17-year-old idiot back then, when we used to have those glass thermometers that contained what inside of them? Mercury. We would all never bring your thermometer from home. My mother probably went, why are we losing our thermometers? John would take them. We would sit there and crack them and spill the mercury on the table. Like I said, I am not endorsing this video rule. But it was, I wish at the time we had the capabilities to record that action, because we would sit there and try to separate the mercury with my own hand. Separate the mercury, and we'd watch that liquid go, and we'd separate it again, get close enough together, it had that attractive force between itself. Slide it across the table, it would all fall together, as opposed to I put water on the table, it's gonna go wherever it wants to go, right? And so that is the attractive force between these like molecules wanting to hold together. Okay, so this represents mercury, liquid mercury, versus this is water. All right, a few other terms here. Sorry for all the terms from this chapter here. So, but boiling point. We know when we heat up a liquid to a high enough temperature, that liquid will then boil and turn that liquid into a gas, right? We see that every day when we put something on the stove and we increase the temperature, right? We see that water boiling, let's say. We typically associate boiling point with the temperature that's high, right? I wouldn't want to put my hand and touch the stove when it's that temperature because it's extremely hot. However, if you slide down, the boiling point of most liquefied gases, yes, we can convert gases into a liquid. Liquefied gases is very, very low. Oxygen, gaseous oxygen, we can store, we can save as a liquid oxygen. Now its temperature to remain a liquid has to be extremely cold. Notice the temperature. Has to be less than negative 183 degrees Celsius. I think we can all understand. I can't appreciate how cold that is, but that's extremely cold, right? That keeps that oxygen in its liquid form. But if I allow the temperature to reach negative 183 degrees Celsius or even negative 184, that liquid oxygen will then turn into a gas. We will get to storage of oxygen coming up in a few weeks, in a few chapters from now. But when you think about liquid oxygen, the hospital, it's the hospital. The oxygen that we use in the hospitals, it's all stored as a liquid. In your travels and clinicals, at some point, I'd like you to ask, if you can, if they don't show you, where is the big giant tank on the property where the liquid oxygen is stored? Again, as a respiratory therapist, we typically don't have to go back, we don't have to go out there, we don't have to look at it, but if we happen to be in the right place, right time,
They're gonna look at you and be like, why you wanna
right.
know?
And you get a chance to see it, you will see ice forming on the outside. And it doesn't matter if it's mid-July, August in Florida where it's 1,000,000 degrees hot, there's still gonna be ice forming out there. Why is ice there? Because of how cold that liquid oxygen has to be stored. And we'll get to what it looks like later. I know I have a few pictures that I'll share with you guys in the coming chapters. All right, so when a liquid changes into a gas at a temperature below its boiling point, we call that evaporation. If I was to sit there and pour this water into just a cup, and we measure it, we set it here, we leave it here all week, maybe by Friday, if we looked at the water level, we would notice the water level is a little bit less on Friday than it was today. Well, where'd the water go? Did somebody take a sip of the water? No, it's evaporating. That water is going into the room, into the atmosphere. Temperature influences evaporation the most. The higher the temperature, the greater the evaporation will be. The warmer the air, the more vapor it can hold. Which gets us to talk a little bit about humidity. We're going to start now. So, factors that influence vaporization of water. This picture, or this graph, is from the book. I don't even remember what page I stole it from, but it is from the book. I didn't even write it down, sorry. But in picture A, again, that's water sitting into an open container, and over time, that liquid will begin to evaporate, and that liquid will turn itself from a liquid into a vapor or into a gas. If I was to put a lid over it and cover it, it won't leave the room. It will increase water, vapor, gaseous water inside the container until the point, and again, over time, you may raise the lid and notice there's moisture forming on the bottom of that lid. But over time, we will notice that, okay, there is water, vapor in the air here. But as soon as the air is fully saturated, any excessive water vapor will return back into the jar in its liquid form. Okay, so as soon as the air is fully saturated with water, the air can't hold any more water. That water vapor will return back into its liquid form and fall back into the container. Now, what's the greatest influence we have on evaporation? Temperature. If you heat this liquid, you will significantly increase evaporation and increase water vapor. We know that with our humidifiers. I don't get too much into the equipment yet because we have a whole chapter on that. But when we have a humidifier and I heat a humidifier, guess what happens to the moisture output? It significantly increases if we're trying to really help our patients humidify the gases they're breathing in. If I was to cover it, again, I can still increase evaporation, but now I can actually measure and see an increase in water vapor pressure. Water vapor pressure. All right, so go back to what increases evaporation the most? The temperature. Increasing the temperature or heating the object will significantly increase evaporation. All right, some terms here related to humidity. All right, the term absolute humidity. This is known as its water vapor content. We're talking about a physical amount. How much moisture? It's its absolute humidity. That's an amount of moisture we're providing. It's the amount or weight of water vapor in a gas measured as in milligrams per liter. Milligrams of water per liter of gas is what it actually is. That can vary with temperature and pressure. Some of this we actually know already, just didn't know you know it. Air that's considered fully saturated with water vapor has an absolute humidity of 43.8. You remember the number I shared with you guys before and I just said 44? I'm cool, round it up. Round it up, it's easy to remember, 44. 43.8 milligrams per liter of water at, what's so special about 37 degrees Celsius? That's normal body temperature. 760 millimeters of mercury. You may know what that number represents? 760 millimeters of mercury.
Pressure.
It's a pressure. Anybody have a clue what pressure? Starts with a B. Good guess, good guess. Barometric pressure. Barometric pressure. So, again, I'll call it the 44 milligrams of water per liter of gas at normal body temperature, normal barometric pressure, and at a water vapor pressure of 47 millimeters of mercury. Now, careful on that one. The students get the 44 number and the 47 number mixed up all the time. And I get it, the numbers are very close, but they represent two different things. What's the 44 represent? Humidity content, the amount. What's the 47 represent? Water vapor pressure. And so I'm going to simplify it even further. The 44 is an amount, milligrams per liter, an amount. The 47 is millimeters of mercury, mmHg, which represents pressure. So 47's the pressure, 44's the amount. Both definitions have water in them, hence added confusion. Sometimes people get those mixed up, and you know I'm going to do it when I ask one of those in a question. I'm going to give you 44 as an answer, and I'm going to give you 47 as an answer to pick from. And I sit back and I sit back and I watch, and I'll say, let's see who I confused. Let's see, or who I tricked on that particular test question. When we'll go over it more, we'll continue to talk about it. We'll talk about it again when we get to humidity. Don't worry about this chart, but I did want to point out at different temperatures, there's different water vapor pressures and different water vapor content amounts. Again, at various temperatures. So sometimes when you say, well, what's the content, or what's the amount, or what's the pressure? Well, it does vary based on temperature. What's important to us is at normal body temperature, and I know you guys in the back probably can't see it, but at 37 degrees, 47 is the water vapor pressure, whereas 43.8, I'm going to call it 44, okay, 44 is the content, the amount. Okay.
Where does this take on?
It's from the book somewhere, I don't know, I don't remember. I would help myself to help you if I would have jotted down a page number, and of course I'm looking at everything I've written down, and I didn't put a page number on anything. I'm trying to be I'm trying to improve myself, to be honest with you. Shocker. And I'm moving away from using a physical textbook, and I'm using a digital one. It's hard. It's hard for me to do this. And so when I'm looking at it, I don't notice the page number. Now I know the page number is there at the bottom of the thing, and when I'm scrolling, I never realized as I'm scrolling, I just flipped 6 pages as I'm scrolling down. And so I know the page number is there, but it's not as obvious when I do that to me as opposed to when I turn the page physically. So part of this is my issue because I'm trying to utilize, when I'm putting these things together, I'm trying to use the digital textbook. Trust me, you guys don't like carrying that big ass book around. I don't like carrying it either. And it would leave from here, home, back again. I'm like, oh my God, I feel like a student carrying all these books. So the digital version goes with me wherever I go. So I'm trying to be good about that, but now it's my fault because I'm forgetting to jot down page numbers as far as where I'm at. The other class I do a better job because I do kind of jump around the book a little bit, and I want to make sure I'm telling you what we're omitting or what's being included. This one I kind of did not do that here, so I apologize. It is what it is. All right, term relative humidity. Relative humidity. So absolute humidity again, looking for a content amount, milligrams per liter. Relative humidity tells us the amount divided by its saturated capacity. So the answer will be a percentage, not a physical amount number like milligrams per liter, but an actual percentage. And it's based on how much it's holding versus how much it was capable of holding. And I'll give you an example here in just a second. So it's really taking this content or its absolute humidity and dividing it by its saturated capacity times 100 is just to make it look right on your calculator is all it is. So let me give you an example. Question is, what would be the relative humidity if a gas held 22 milligrams of water per liter when the saturated capacity is 44 milligrams of water per liter, again at normal body temperature? I give you actually the image of it. Okay, so if it's capable of holding 44, that would be classified as 100% saturated, fully saturated. In my example, we're only holding 22. What would be its relative humidity? Again, it's right now it's holding 22, but it's capable of holding how much? 44. What would be its relative humidity? 50%. So 50%. 22 divided by 44. 22 divided by 44. Sorry, I didn't put the answer there. But it would be 50%. It's down here, there at the bottom. 50%. Sorry, I know I hid this slide from you guys. Didn't want you to solve it ahead. So I don't care how I can ask the question. I can give you whatever number here. I would have to tell you, well, what is its saturated capacity? I would have to tell you that. You wouldn't be expected to memorize that number because it could be different on various temperatures. So again, I just did this example because it's easy. I don't necessarily calculate or punch it in to see it, that it's half. If I gave you one that's, say, 11 milligrams, that would be about 25%, right? 11 divided by 44, or 25%. Everybody okay? Yes.
Where are we getting the 100 from?
That's what, to be considered fully saturated,
Oh,
100% saturated, 100%.
Oh, gotcha.
Now again, that 44 number in this definition could change. That's why I said I would have to tell you what the saturated capacity is.
But you would always times it by 100, right?
Yes, again, and all that is to make it look right on your calculator.
Okay.
Because if you didn't, it would say 0.50. Now, some of you can look at 0.5 and realize, okay, that's 50%. But if you it has to look right on the calculator, then times it by 100, then we'll say 50. Okay, so that's completely up to you and your comfort in fiddling with that little bit of math. All right, so let me move on from this. Got another example here in just a second. So, when water vapor content of a volume of gas equals its capacity, its relative humidity is 100%. Okay, It's carrying everything that it can. When the relative humidity is 100%, gas is, like I said, fully saturated with water or fully saturated with water vapor. Now, if we allow the gas to cool, again, the moisture is in the air, but we're allowing the gas to cool, guess what's going to happen to that moisture? It can convert from its vapor or gaseous form back into a liquid. We'll get through better examples of that when we talk about heat, humidity, the equipment, because one thing we encounter in practice, and I'll mention it again when we get to it, when we allow a gas to cool and that water vapor that you can't see with the naked eye, when we allow the gas to cool, that water vapor turns back into a liquid, and so we'll see that liquid inside of our circuitry. And usually we don't want to have liquid inside the circuitry. We want to have gas or air inside that circuitry. So that's a problem we will discuss a little bit further, but it's going to be related to this. Allowing the gas to cool will then allow condensation to form inside our circuits, and we don't typically ever want that. Which I think I just hit that second bullet point, sorry. All right, let's talk about where it really matters to us. So we defined absolute humidity, that's the actual amount. We defined relative humidity, that's the actual amount divided by its saturated capacity. And I'm going to take relative humidity and tweak it just a little bit, and we're going to use, instead of relative humidity in clinical practice, we'll use the term body humidity. Body humidity. So the formula is still the same, content divided by saturated capacity times 100, except when we say body humidity, God bless you, we know what the body requires is that 44 number. The body requires how much moisture? 44 milligrams of water per liter of gas. So when we use the term body humidity, we already know the 44 is here. I don't have to give that to you in the question. I am not going to give that to you in the question. I'm going to expect you to know it. But I will say the humidifier we selected for our patient provides this much content, this much moisture. What is the body humidity? Well, you're going to take this number from the question and know you're going to take that number and divide it by how much? 44. So that using body humidity. We will get into that too when we talk about our humidifiers.
So you would give us like a formula like that, just omitting the body heat, and expect us to know that to calculate the formula out? Or
Body
is that what you're
humidity.
saying?
Body humidity. Body humidity. So, yes, so I will tell you the humidifier we selected is carrying whatever the number is going to be.
Okay.
This amount. The content of this humidifier is, and I'll use the previous example, 22. Okay? What is its body humidity? Now, I didn't give you the saturated capacity. You have to remember, because we're talking body humidity, what the body requires is 44. So that's its saturated capacity all the time. It's still the relative humidity formula, except specific for the body. Whereas we know with relative humidity, change the temperature, you're going to change the saturated capacity. But this we know, well, what does the body need? The body needs normal body temperature carrying the 44 milligrams of water. My question to you is, on the test, we randomly picked this humidifier that provides a certain content, and that's all it provides. What is this humidifier body humidity? What is it capable of providing to the patient, body humidity wise? And so it's whatever the number I give you from the humidifier divided by 44. And that will tell us what the body humidity is for that particular humidifier. I'm not getting too much into it now in this chapter per se. Yeah, I may give you one question on the test, and I can't say I honestly am or am not. When we get to humidifiers, I absolutely will, because we have to know the different amounts here of the various humidifiers, which in turn leads to, well, what is the body humidity the various humidifiers are capable of providing. I saw the hands go up.
If we use the 43.8, would it be the same number as the 44?
Essentially. But I'm going to tell you right now, I'm going to use 44. So when I'm trying to solve an answer, I'm going to use 44. Now technical number is 43.8, but I'm gonna use 44. So if you use 43.8, you wonder, you know, my answer is not exactly like the answer options John gave me. That's why, because I used 44. Sharon, I saw your hand. Go ahead.
You answered my question,
Okay.
thank you.
Does the TMC use 43.8?
No, they'll use 44 as well.
Oh, okay.
Okay, yeah. No, trust me. If MBRC was gonna use it, well then, sorry guys, you have to use 43.8. And there's times, and I'm glad you guys asked that question, because it's gonna come up multiple occasions. An answer may come out to be something, point something. Do I have to, is it okay to round that up, or round that down, or do I have to use that point? There's sometimes, yeah, we really should use the decimal point number. And then there's other times like this, it's okay to round up. We'll get close enough to what the right answer is. But if you're one of those people that has to be exact for everything, I mean, I get it, that's nothing wrong with it, I'm really the same way. But where I can round up and still get the correct answer, I'm gonna say, let's do that, because it's gonna be less hassle for you to have to memorize some of those points. But like I said, some of the things we do, yeah, we are gonna have to memorize a decimal point for some things. It's when we can get away from not having to do it that I try to. Heck, I would have given you 44 from the get-go if the textbook didn't use 43.8. And I know if I left it 44, at some point somebody's gonna say, but I read somewhere it's 43.8, so I went ahead and left it here. But just understand, if you're looking at the answer options I'm giving, I'm doing the math and I'm dividing whatever the number is I gave you by 44. That's where I'm getting my answer options from. All right, any other questions? All right, switching gears just a little bit. Properties of gases. Now, diffusion of gases. So by definition, diffusion is a process where molecules move from areas of high concentration into areas of low concentration. That is the textbook definition for diffusion. And what we're talking about here is really diffusion of gases, diffusion of oxygen, and in time we'll talk about diffusion of carbon dioxide even. But right now, let's talk about diffusion of oxygen. So we know already because of discussion that gases have high kinetic energy. That allows them, again, they're in constant motion. They diffuse very rapidly, do gases. That's why, thank goodness, the oxygen that's in our alveolus quickly diffuses into our bloodstream to provide that oxygen to the body and to the tissues that need it. All gases do exert pressure. You may hear the term tension used. What is the oxygen tension? Okay, that's describing the oxygen amount that is there. Terms like partial pressure could be used here to describe oxygen. That would be the pressure exerted of a single gas in a gas mixture. Now the units here, millimeters of mercury. Millimeters of mercury are measurements of pressure or tension. You can also perhaps see the acronym TOR, T-O-R-R, just so you guys are aware. And I try to be as consistent with how knowing you guys would be tested from the MBRC. Unfortunately, as it looks right now, MBRC for some questions will use millimeters of mercury, and in other questions, sometimes use the word torr, the unit, torr. Now, they're the exact same thing. So there is no factor to try to change, you have to change the number. So don't let millimeters of mercury or torr completely throw you off your game. The number is exactly the same. The unit definition would be slightly different, I guess, but the number does not change. So you can use millimeters of mercury and torr almost synonymously back and forth. And so sometimes you'll see my questions, just so you guys are aware, I usually use millimeters of mercury. But sometimes you will see some MBRC questions throw in torr in there, and that may be something that, I don't remember us using that number, that unit for anything before. The number's still the same. So don't worry about trying to memorize a different group of values. All right, please don't hurt me too bad here. We're gonna talk about several laws, and it's easy to get the laws sometimes confused or mixed up. All these different people's names, they all had to come up with their own special thing. Law. So this first one is Dalton's law. Yeah. His law describes a relationship between the partial pressure of individual gases and the total pressure of all the gases that may be in a particular mixture. The total pressure of the mixture of gases must equal the sum of each one of those partial pressure components. So using this, if I know the different pressures of all the gases in a mixture, and I was to add them up, that would equal the total pressure. That's what Dalton's law is, describing all of those individual pressures in a gas mixture. Now, let's talk about the gas mixture that is in the room right now that you and I are breathing in. Okay? What gases are in the room right now that you and I are breathing in? Oxygen, nitrogen, argon. Very good. Nobody ever gets argon. Carbon dioxide, helium. That's the mumble.
No, I was saying helium, but
Okay, sorry. Helium, and there's other trace gases, but which one is the largest amount? Nitrogen. What percentage?
78.
About 78-79%. How much is oxygen? 20 point something, 21 if we round up. So you take 79 and 21, you add them together, that's 100. All right? That would be the number over here. But we know we're rounding up when we say 21, we're actually rounding up just a little bit. When we say 98, we're actually rounding up just a little bit. It's actually 98 point something, and it's actually 20 point something for those two, which leaves us generally less than 1% to be everything else. So if we look at what's in the gas mixture, again, 78% nitrogen, 20.9, and yes, I'm going to round it up and call it 21, damn it, for anybody asks. 21% oxygen, and the other few trace gases that are there. Okay? The other few trace gases that are there. According to Dalton's law, you add all of this up, or all of this up, what will it equal? The total barometric pressure. Again, assuming you and I are at sea level like we are right now. So when you see some of these numbers, 592.3 or 159.6, that's the amount of nitrogen, that's the amount of oxygen. Now, where did that number come from? Remember when we said before, well, what we're breathing in right now in the room, what percentage of that is oxygen? And we said 21%. Well, it's 21% of what? The total. And so, if I did my math right, and you can always double check me, 21% of 760 should equal 159.6. We can round, I don't care, we can round it up, call that 160. That's okay. 160 millimeters of mercury. And so this is an important number to remember. Because now that we know, when I say, well, what's the oxygen concentration in the room right now, and you say 21%, I know everybody and their brother in this room knows it's 21%. But I'm going to ask it a different way. What is the amount in millimeters of mercury of oxygen in this room right now? You can't tell me 21 anymore. But you can tell me it's about 160, again, rounding up. 159.6 or 160. Okay, so think about it. You and I breathing normal right now, and we're no distress, we're breathing quite comfortably. How much oxygen are we breathing in from the room? Don't tell me 21. Tell me we're breathing in 160 millimeters of mercury of oxygen in the room right now. That's what our bodies need to breathe in. You give me less than that, you give me less than 21%, then that's not normal for you and I to breathe in, correct?
The 760 is just normal, but it doesn't always stay like that.
Correct. That's normal atmospheric or barometric pressure. Normal's at sea level is 760. You go up in elevation, you live in a mountainous area, what happens to this number? It goes down. And so, I'll use Denver, Colorado. How many feet up is Denver, Colorado? Mile high. What, 5,200 and something? A mile high. The barometric pressure in Denver, Colorado is not 760. It's in the low 600s. Don't quote me on the number right now. I'm going to look that up. But it's 600 and something. Well, how much oxygen is in Denver? Well, it's 21% of that number.
So it's still gonna be.
So it's gonna be,
21% and still
it's still gonna be
78%.
21%. But in Denver, where the barometric pressure is 600 and something, and we'll do some math here in just a second. We're at 600 and something, I know, oh goody, and you're breathing in 21% of that atmosphere. Okay, I bet you your number's not gonna be 160. That's why if anybody has ever visited Denver or Colorado, maybe normal exertion, I don't notice anything, but you start to do anything physical, walking, hiking, whatever, because this amount is not quite what you're getting there, that's why you get winded. Even if you're normally healthy, perfectly healthy, it's because there's just not as much oxygen there. Is the 21% different? No, it's still 21%, but it's 21% of that barometric pressure. Did I see another hand or
Oh, no, I was
thought
gonna say,
about?
not that you were asking, but it's 6:15.
Okay,
Yeah.
the barometric pressure
I just
there?
wanted to
Okay.
know, yeah.
Gotcha. Can't sleep at night if I don't know.
Yeah.
All right. So the other numbers are fine to know, but it's really this oxygen. Because ultimately, where we're going to be going with this in time is looking at how much oxygen is actually in our bloodstream. And if this is what's available, and in time we'll learn how much should be in the bloodstream, we'll see how much of it actually diffused into the bloodstream.
So you're saying that, not to get ahead, like the 98% like oxygen saturation, like if you're wearing like a full socks,
Mm-hmm.
is that what we're gonna be talking, is that like in relation
That's
to that?
different.
Okay.
Oxygen saturation is different than what this represents. Oxygen saturation is an indirect measurement, or the pulse oximeter, I should say. Saturation is an indirect measurement of how saturated your hemoglobin is with oxygen. It's not this.
Okay.
That's different.
Okay.
That's different. Interrelated, yes, and we'll get to that in time, but it's not the same. It's different. All right. If you've ever flown before, right, and you sat through the pre-flight instructions, which if you look around the airplane, 75, I'm being too generous, 90% of the people are not even paying attention, right? They're busy doing whatever, the headphones in, not even listening to the instruction. If I was a flight attendant, I would be so pissed. You're gonna pay attention, you're gonna listen to me, damn it, put that stuff down. But that's just me. I'm taking off points, you're not getting your grade. So, during instruction, safety instructions, one thing they tell us is that an oxygen mask could deploy from the overhead cabinet there. Okay, hope it never does, but it's there for, it will deploy for a reason. And they'll also, before I ask the question, they'll also say, and if it does, put it on yourself before you assist any others, including children. Put it on yourself first before you help anybody else out with their mask. Okay, so when and why would these things deploy, and why is it important?
Because they adjust the pressure inside the plane to be atmospheric, and if something happens, it changes, we need the oxygen.
Okay, yeah, that's exactly right. That's exactly right. So when we fly, and how high do we go when we fly? 30,000 plus feet in the air. Where the barometric pressure, guess what? It's not like it is at sea level. And so, what's up with the airline? What's up with our plane? They're pressurized. That cabin pressure. So their instruction says, if we, unfortunately, how do they phrase it? In the unlikely event we lose cabin pressure, mass will deploy. Because if we lose cabin pressure, and now we have the same pressure as what's outside the airplane, what happens to the barometric pressure way up high? It's much less than it is here, which means we still would be breathing 21% of whatever the pressure is up there, which is going to be significantly less than it would be here. And why do they tell us to put it on ourselves before we help others?
So we don't pass out.
Before you pass out. Because if you're not provided the oxygen that you need, you will pass out, including the pilots. I guess they're the most important people that need to make sure they're putting their oxygen masks on, because they're controlling the plane, and they could get us down to a lower elevation where the barometric pressure is not so high, and the oxygen amount wouldn't be so low. All right? So, play with a little math here, and I've done the math here, so you can kind of listen along. At 30,000 feet, and you know, there's planes that go higher than that, but at 30,000 feet, the barometric pressure is approximately 226. That means when you're breathing 21% oxygen, room air, you're only going to get 21% of that amount. All right? When, what are we normally breathing right now? What is that amount? 160, right? 160?
About 40 something.
So that's all you get. That's all you're going to get if we lose cabin pressure at 30,000 feet. When your body needs how much?
160.
160. That number at normal barometric pressure. No wonder we pass out in a matter of seconds, right? There's not a lot of time. You're starting to breathe in, instead of breathing in this, you're breathing in that. You're going to pass out very quickly. That's why I put the mask on yourself. Then you can help other people with their mask. When that oxygen mask deploys on the aircraft, it typically provides around an oxygen concentration of 70%. So if we were to say, okay, if that mask with the bag on the end of it provides around 70%, well, how much of it will I get? And still, I'm at 30,000 feet. Close, that's 158. That's pretty close to what we're getting here right now. And so that's why that gives us some time to stay alert, to scream bloody murder, because why in the hell do we lose cabin pressure? But nevertheless, I can at least still stay conscious and can still help others around me. You know, kids, passengers that are next to me. Now again, the distance, I can't go up to the front of the plane. That mask is not going to stretch that far, but at least I can help people next to me with their oxygen. All right, so that's why we have oxygen that would be deployed. And again, really my main concern is the pilots better have on their oxygen so they can get us down to a safer altitude where the barometric pressure is not so low. Mount Everest, those crazy nuts that have to climb the peak of Mount Everest.
Completely optional, by the way.
Yeah, absolutely, better be. It would be the best photo op in the world, but to get there, can somebody drop me up there and get me that photo and then safely get me back down somewhere? Barometric pressure, again, gonna be that low. So how in the world are those people able to ascend where there's ice and snow everywhere, to physically be able to navigate that past all the trash and bodies that are left up there from the people that weren't able to make it, and still only receive this much oxygen? But what are the people that are ascending to Mount Everest wearing?
Respiratory.
Oxygen. Pressurized oxygen masks, like CPAP masks, but with oxygen. So aside from stepping over the bodies, it's all the oxygen tanks that they leave behind up there. It's crazy. You go back several decades, you could probably count on one hand how many people were actually able to do it. Now people, one, in better shape, but two, all the supplemental stuff they can bring with them. But what about the guides? What about the Sherpas that help those folks climb, that do all the physical work? And that's why those people paid, I don't know what they paid, thousands, millions of dollars
It's
to
like
do
$35,000.
that. Yeah, I mean, it's a whole tourist thing that helps the Sherpas in Tibet be able to afford to do whatever. I wonder, I don't know the answer to this, but I wonder, what is the viscosity of their blood like? Because they live there. They're not flying there from some rich country to go climb that and pay millions of dollars. They live there. I wonder how thick their blood how viscous their blood must be. Because they do, that's their occupation. That's what they do, is take these rich tourists up to the mountain, and hopefully people survive, but it's crazy when the barometric pressure is that low.
So whenever we breathe in the 21% of oxygen, we're only actually metabolizing 16% of the air, in our lungs, right?
And we'll get there. We're just, what's available to us is 160. I didn't say that's how much ends up in your lung. but what's
Okay.
available
But
to us is 160.
But it's like 16% of whatever is available. Not like, I guess I'm trying to think of how to like ask this question.
He's like, do I?
But, yeah, right, cause it's like, I don't know, we're only getting like 16% of it, so like, but it's only 16% of the 47.5 for like being up in the air, or it's only 16% of like the 159.6.
Okay.
So, but it's not like 16% of like the 21%, you know what I mean, like,
Right. I gotcha.
so like no matter how, so it's like not dependent on like how much oxygen like you're breathing in, like if somebody's on like a nasal cannula, or
Well-
something like with like oxygen and stuff, like it matters how much they're getting, because we are getting 16% of that number, not just
Right.
metabolizing 16% of the 21, not like,
Right, let's talk about what we're getting, not necessarily what we're metabolizing yet, but what we're getting. So if this is what we would get, again, 30,000 feet, just breathing room air, but we give you oxygen, I'm upping that percentage. That's why we're seeing a number close to normal that the patient's receiving. What about your patient in the hospital that is here, okay? They're into the hospital, they're breathing the same amount of air as you and I are breathing, 21%, and they're at sea level. That's what's available to them, but because of their disease and illness, it's kind of getting to your metabolism part, but I'm not gonna use that word, but what actually gets into their body is much less, okay? They don't quite get this, and you and I don't get this much. It's available, but once, and we'll get to all those steps in due time, once it gets into the bloodstream, that number, just to fast forward, is about 100. What actually gets into my bloodstream, normally. But now you throw in somebody who has COPD or some other illness where they're not able to get that amount, and now, even though this is available, what they're only getting in their body is maybe 60, just to pick a number. Well, how can I bump up that 60? Give them more oxygen. Give them a higher concentration of oxygen. And that's gonna obviously bump up this number, but if I need to bump up this number to get more oxygen into the bloodstream, that's what we have to do. And that's why we put those patients on oxygen.
Wait, so I'm confused, where did we get the 16% from?
We didn't.
Oh, okay, that.
She's doing some math here.
Oh,
It's
okay,
It's okay.
I definitely can't do that.
Nope. All right, let's move on. We can spend the whole afternoon talking about this. All right, so hyperbaric chambers. So instead of having a patient with a low barometric pressure, we can put them in a hyperbaric chamber and do what to barometric pressure? Raise it. And so it actually increases how much oxygen they could inspire. So it has a kind of the exact opposite effect of going up in elevation where their barometric pressure is lower, and the oxygen they would be able to breathe in is going to be much lower than it would be at sea level. In a hyperbaric chamber, they physically don't go into the earth, but we put them in a chamber to simulate as though we were dropping them down into the ground, into the earth. And what we're doing is raising barometric pressure. And so I'm going to skip forward here just a second. We can actually drop them down, not literally, but figuratively inside this chamber, raise the barometric pressure to over 2,000, instead of 760, over 2,000 millimeters of mercury. If they breathe in room air, how much oxygen are they going to get? 179 instead of the 160 you and I are getting. And so, 479, sorry. So 479. So notice how much more oxygen is available to them when they're inside the chamber. Okay, so going back here, decompression sickness can be used. It helps get the nitrogen bubbles out that's accumulating into the bloodstream for a diver that ascends to the surface too quickly. Carbon monoxide poisoning, that's CO, carbon monoxide poisoning. Gangrenous wounds that won't heal. It's amazing when you see patients who have maybe lower extremity wounds that aren't healing, decubitus ulcers that aren't able to heal. These could be diabetic patients who have trouble just getting adequate blood flow to their extremities. And just even the simplest nick or cut on their leg can be turn very nasty. By putting them in these higher oxygen environments for therapy, for treatment, actually can help out the patient. Now notice my example here is just breathing room air. Couldn't we still give this patient supplemental oxygen? We sure could. We can give a patient 100% oxygen. We're raising this up to 2,280 millimeters of mercury, as opposed to you and I breathing in 160. Again, really creating an increased environment of oxygen available to the patient. So hyperbaric chamber is kind of the exact opposite concept of going up in elevation, because it's almost like you're going down into the earth. And I don't know if you can even tell my picture here. In hyperbaric chambers, they have some hyperbaric therapy can be in a singular tube where just a person gets into it. I'm not a claustrophobic person, but you put me in one of these tubes, I think I may get a little jittery. I've never been in one, so I don't know. Because they're clear, so you can see outside, but the pressure is going to be much higher inside. Anybody ever go to the bottom of a swimming pool or dive? What happened? What does it feel like in your ears? You feel that pressure? All right, so popping the eardrum is one potential complication, but you feel that pressure. This is a multi-chamber where you can have multiple patients inside, all receiving the same therapy. Now notice the little helmets they have on connected to oxygen, so they can be receiving various oxygen concentrations depending on what the patient's needs are, but they all are technically going down where the barometric pressure is much higher. I don't know if I use this example with you guys, but my joke always with hyperbaric therapy is I want to do a study. I want to test 2 respiratory therapy students that academically are essentially the same. However, one studies inside here where the oxygen environment is higher. I'm just thinking more oxygen, more synapses will fire, as opposed to somebody studying outside of the chamber. I would love to be able to do a study and see, does it actually help you retain information? Again, trying to find the 2 equal students is the hardest challenge. But it would be interesting to know if something like that would exist.
There was ever an accident or something with too much pressure on those cabins, like, I think I'll be afraid to.
Of course,
Like
of course. Without getting too much into it right now, of course, and it's true with anything, there is potential complications and hazards. Excessive pressure, like I said, I use the bursting of the eardrum just being one affecting the patient, but you would obviously have to be cautious for sparks, flames, that sort of thing. But yes, if anybody was to, and there's some of these bigger chambers, and not everyone, but in some of our larger hospitals in town, if you ever find a wound care clinic, wound care clinic, you may be able to find hyperbaric chambers in those places, again, to aid in the healing process. I remember at St. Vincent's, and I don't remember what floor it's on, it's Riverside, but where they actually had to take part of the wall out, I want to say in the Dillon building, because somewhere up there on one of those upper floors is a wound center, and I remember seeing videos or pictures of it, of them bringing in the hyperbaric chamber through the wall, because again, they can't bring it up from the ground floor, the chamber itself is too big, but up there. But yeah, it's interesting ideas, interesting concepts here with the hyperbaric chambers. All right, let's talk about gas laws. More laws here, so I apologize. More names to remember and more things to get confused.
We're in law school.
Yeah, we're not in law school. Yeah, sorry. So, several laws help us define the relationships among gases, specifically their pressure, temperature, and volume. And here's the folks that we need to know. Boyle's, Charles, and Gay-Lussac's law. Using these laws, the behaviors of gases under changing conditions can be predicted, which we would refer to them then as an ideal gas. So we'll talk about each one. The first one is Boyle's law. Boyle's law. Boyle's law states that with a constant temperature, That's important to remember. Constant temperature, the volume of a gas will vary inversely with its pressure. Meaning if the volume goes up, the pressure will go down. Or if the volume goes down, the pressure will go up. Again, inverse relationship between volume and pressure. Charles' law. Charles' law states that if pressure remains constant, then the volume of a gas will vary directly with its temperature. Meaning, temperature goes up, volume goes up. Temperature go down, volume will go down. Again, direct relationship. The third, Gay-Lussac. Now, the Gay-Lussac's law, he states that if volume remains constant, then what are the two remaining factors? Volume constant, what we're left with to look at is temperature and pressure. Just like the previous one, they also are directly related. If pressure goes up, then temperature will go up because volume's constant. If temperature goes up, pressure will go up, and vice versa. Temperature goes down, the pressure will go down. All right, so with all three of those, the biggest factor, or one of the biggest factors to remember is what is constant. Remember, there's three things we're looking at: pressure, volume, and temperature. Which one is constant? Once you get the constant part, then the two remaining factors, how do they relate? Boyle's is the only one that goes kind of opposite, that varies inversely. The other two, they vary directly. One goes up, the other goes up. One goes down, the other goes down. Totally confused now? Good, good. That's what I was hoping for. All right, so I'm not putting this up here to try to be offending by any means, but what I just said about those laws can be extremely confusing. Yes? Yeah. You just heard me talk about it. If I give you a test right now on those three gas laws, I'm lucky if we get a 50%, right? I know it's the first time you heard about it, but again, there's a lot of things that are interrelated. Something's constant, the other two things are going to vary directly or inversely, but it's hard to keep them straight. So, I'll say this. I can't claim ownership of it. It's not mine, but it was something umpteen years ago that was taught to me, and it stuck. And so I'm going to share it with you, okay? It's looking at pressure, volume, and temperature. Pressure, volume, and temperature. Now remember, these three gas laws, Boyle's, Charles, and Gay-Lussac's, are dealing with the relationship between these three factors. But remember, one of those factors has to remain constant, and then we're looking at the other two. And again, my shortcut doesn't help you with how the other two behave. You have to know which ones are inversely related, meaning they're going in opposite directions, versus directly related. So, my analogy uses baseball. I'm a baseball guy. I was a baseball player back in my day. Loved the sport. And so my baseball analogy is this. And the hat. I'm from San Diego originally, and so I'm a huge San Diego Padres fan. So hence why I use a San Diego Padres hat in my example. All right, what is this thing? A bat. It's a bat. What is this thing? Cap. It's a cap. Very good. Cap. I know it's a hat. I call it a hat too. But in my example, it has to be a cap. This is a glove. Okay, so bat. B-A-T. The T in bat, and actually let me start over. The B in bat stands for Boyle's. Boyle's law. The T represents temperature. That's what's constant in Boyle's law. Temperature. So if temperature remains constant, the other two factors are pressure and volume. Now how do they behave in Boyle's law? Inversely. Opposite directions. So if temperature is constant, pressure goes up, volume goes down, or pressure goes down, volume goes up. Again, they're going in opposite directions. That's Boyle's law, the bat. Now we said this was a what again? It's a cap. C for Charles. The P in CAP represents pressure. That's what's constant. Now the two factors that are left behind are volume and temperature. How do they behave? They're direct. Volume goes up, temperature goes up. Volume goes down, temperature goes down. According to whose law? Charles' law. The C in CAP. Now the glove, the G in glove stands for Gay-Lussac. All right, so the G in glove stands for Gay-Lussac. The V that's in glove represents volume. That's what's constant in Gay-Lussac's law. So now we're left with pressure and temperature. How do they relate? Directly. Temperature goes up, pressure goes up, temperature goes up. Pressure goes down, temperature goes down. Okay, remember, it's only Boyle's law where they go opposite directions from each other. But that I always say, you've got to know what's constant first. You have to know what's constant first. In Boyle's law, temperature is constant. Charles' law, pressure is constant. Gay-Lussac's law, volume is constant. The rest of it is on you to remember how they relate, right? This is the only one where they're inversely related. The other two, they're directly related. Does that help a little?
Yes.
Okay. Like I said, that was taught to me many, many years ago. And so I'm like, that's still to this day, that's how I have to keep them straight. I can't sit there and just memorize it and think, okay, I'll remember it tomorrow or the next day or the next year. I got to keep it straight. As I'm up here babbling my little script, in my mind I'm thinking back cat glove, back cat glove. Don't get them confused, John. Back cat glove, back cat glove. Fun stuff, I tell you. All right, so let me do the questions, and then I'll be happy to answer any of your questions. All right. First question is, what is the change of state where a liquid is converted into a gas? Is that evaporation, condensation, sublimation, or is that melting point? Change of state where a liquid is converted into a gas. That is evaporation. Correct. Evaporation. So A. Are we okay with that one? Next question. Here we go with the laws. Whose law states that the partial pressure of a gas in a mixture is proportional to its percentage in a mixture? Was that Gay-Lussac, Charles, Boyle's, or Dalton's? That is Dalton's. And I didn't say this when we went over Dalton's, but I always say in myself, or at least in my head, it's Dalton's law of partial pressure. That's not what I'm going to give you as an answer option. I'm just going to simply say Dalton's. But it's Dalton's law of partial pressure. All those parts and pieces of the gases in our atmosphere, add them together, that equals total barometric pressure. That is Dalton's law. All right, two more. Another law, whose law states that with constant temperature, the volume of a gas varies inversely with its pressure? Again, remember I said what's constant? Temperature is constant. Of that bat cat glove analogy, that's Boyle's law. Boyle's law. Again, the T at the end of bat, B for Boyle's and bat, the T represents temperature being constant. But remember, I can alter these questions ever so slightly and tell you, okay, it's constant, but how do these two things behave? That you remember it's for Dalton's, or excuse me, for Boyle's, they're inversely related. The other two, they're directly related. All right, one more. Whose law states that with constant pressure? No, I said constant pressure, so whose was that? That's Cap and Charles, sure.
Cap and Charles.
All right, hopefully the shortcuts helped a little bit, make some semblance of sense there with the relationship between pressure, volume, and temperature.
I feel like a team.
And I know it's going to take time to review it and hear it over in your head again to have it stick and make sense. But that is really the little bit of physical science discussion. Be honest, I was trying to find, and this has been many, many years, trying to find, well, where can this stuff be brought up in the cardiopulmonary A&P class? And guess what? It's really not in the A&P book. And so that's why I kind of left it here, because I really feel like a lot of this content seems like it's stuff that we talk about more in the cardiopulmonary A&P class, but this information is not really found there. But nevertheless, this kind of finishes chapter 6. On Wednesday in this class, we will fast forward from chapter 6. We'll jump about 30 plus chapters, and start with chapter 37, which is airway management. Now, the airway management chapter, and so Wednesday we actually get to talk about some stuff that you will be doing in time clinically, and happy to say then that means this Friday we have something you can actually do in the lab, which you can't really lab these things that we talked about today, or the ethics can't really lab that, but so this Friday we do have a lab. This is a reminder, we do have a lab this Friday, but it's part of the discussion we're going to talk about on Wednesday from chapter 37. Now, chapter 37 is a long chapter. Airway management, there's all kinds of things that are found in that chapter. Again, us being respiratory therapists, we have to understand and know a lot about the airway and the equipment that we use for the airway. So Wednesday will just be really the start of that discussion. Like I said, we'll be able to have some things that we will learn Wednesday that we can actually then see and apply to situations or scenarios or equipment, like I said, for this Friday. But chapter 37, the airway management chapter, is actually 3 parts. This Wednesday, we just do part 1. And then we still have the following week 2 parts to continue. And a lab the following week, following Friday as well. So I'm excited for you guys, at least in the fundamentals part, because there's tangible stuff that we will be practicing, that we'll be able to do, equipment that you have to know all the parts and pieces and how to assemble them when the time comes. So all kinds of good stuff that we'll mention then. All right, so I have it 11 o'clock. Okay, it's 11 o'clock right now. Is anyone opposed? We will speak for Gisela because she has to step out for a second. Is anybody opposed to starting the next class 30 minutes earlier?
Not one bit.
So instead of sticking around waiting for an hour,